Okay, let us look to God in prayer. Merciful God, our Heavenly Parent, thank you for this wonderful afternoon. Thank you for giving us yet another chance to come before you and to learn the new avenues and horizons of the research areas and the new scope in the field of studies. Gracious God, thank you for the knowledge and wisdom that you are giving to us. Merciful God, you were with us throughout the last all sessions. You guided us. You gave us the scope and platform to gather together and to listen from learned persons. Today again, as we have come before you, give us the knowledge and the insights and help us to deepen our understandings in our various fields, what we are going to listen. Help us to make the things practical, to internalize things so that it can help our students and to the larger community. Especially we pray for our leaders, we pray for the organizing heads, the one who are leading the sessions. We ask this prayer in the name of our Lord and Savior Jesus Christ. Amen. Thank you.
Thank you, Achan.
Yeah. Good afternoon, everyone. Good afternoon, Simon, sir.
Good afternoon, sir.
Yeah. So we
You can share your screen, sir. You can share your screen and start your presentation.
Yeah.
I also thank the management for the opportunity to enhance our skill in MATLAB. Please share your screen and your start presentation, sir.
Sure, sir.
So today we'll be focusing mainly on transforms, integral transforms, Laplace, Fourier, and Z transforms. All engineering as well as mathematics faculty members will be benefited. Yes, sir, please go ahead.
Yeah, so are you able to see my screen?
Yes, sir.
Okay, yeah. Okay, gentle reminder on the webinar housekeeping that if the participant have any questions during my during my presentation, so you can access chat box to put your question. So we will have Q&A session at the end of the presentation where I will be answering to your questions. So like sir mentioned, today's topic is teaching mathematics with MATLAB. And we'll also be discussing some engineering applications of mathematics, like which are the application areas where where this mathematical the methods are being used, where the Fourier transform is getting used, and what are the what are the applications of it. So this these terms that we are going to discuss today. So agenda is very simple, which I'm going to present today. So the agenda workflow is like, let me open the live script. Okay, so let me zoom in a bit. Yeah. Uh, we'll be starting with a system of an equation. We will discuss how we can create an equation, a symbolic equation in a MATLAB, such as linear one, and how we can analyze that equation, and how we can plot that, how we can visualize that equation using different methods. We'll also talk about Fourier transform and Fourier transform application. I'll also talk a bit about Laplace transform, Z transform. The ODE part, like Simon sir mentioned, they want us to cover ODE part during the PDE session, which is on Friday. So I'm not going to cover most on ODE part, but definitely I would like to introduce this ODE part to you. So I will have one example on single order ODE where I will explain the workflow that how we implement ODE using MATLAB. And I'll also demonstrate how we can use a curve fitting tool, an app that which we have for data fitting applications. So that is the today's agenda. Yeah, so let's get started. That is about teaching mathematics using MATLAB. So a very first example is about a system of an equation where we will solve a system of a cubic and a linear equation using a live editor task. So throughout this presentation, I'm going to use a MATLAB live script, which is a very pretty good combination of code, output, text, the text, symbols, and charts and everything. So which give us an interactive environment for scripting, writing codes in MATLAB and visualizing the output, at the same time. So this is about how we can, define, an equation for cubic and linear, and how we can solve it. So we can interactively solve algebraic equation to obtain symbolic solution using, symbolic match toolbox. So today we will use live editor. So we will use a scripting method. At the same time, we will follow the task as well. So last time I have tried to explain a bit about the task and how we can add on different controls and tasks within this live script, right? So today we will use the symbolic equation task and in the live editor. So let's get started. So today in this particular example, we will implement a system of cubic and linear equation. To solve the system, of a cubic and linear equation, we have this two equation defined, that is x cubed minus 2x squared plus y is equal to 0 and y is equal to 4x minus 8. So here, first of all, we have to define the symbolic variable x and y because we are using, because we are solving an algebraic equation here. So we are using a symbolic match toolbox. So whenever we have to use symbolic match toolbox and I want to solve some equation, I'll have to go with variable declaration. So I'll have to declare this variable as a symbolic variable. So here I want to define that x and variable x and y as a symbolic variable, and how we declare that by using this sims, that is symbolic, sims as this particular function. So sim as is the command used for declaration of symbolic variable, which is x and y. And then we have to define our two equations. So one is the cubic equation, and second is the second is the linear equation. So here we have a cubic equation, that is x cubed. So how we define that? So here we have to use this particular operator. Uh, uh, I can see someone typed in chat box, but I'm not hearing anything. So is this the issue? Everyone is facing the same issue, that I'm not audible. Can you please type in chat box?
Sir, you're audible, but if you can speak a little loudly, it will be better.
I'm using microphone only, sir. Is it better right now?
Yes, now it is better.
Yes, Suraj, means I was able to hear you from the beginning.
Okay.
If anyone is not able to hear properly, I would request them to either rejoin the session, sometimes it is a problem, or connect using computer. Go to the connection settings and hopefully you will be able to hear properly.
And they can also use microphones. They can use headphone. If it is not audible, they can, better to go for a headphone.
Yeah.
Yes, yes, sure.
Okay, I hope I'm better now. Yeah. So I'm defining an equation here, that is a cubic equation and linear equation, and we are using this operator to logical operator to declare the equality sign of the equation, and that is how we declare an equation using in MATLAB, and this is we can say a symbolic equation. And then what we are doing is to declare the system of equation, because our system contains two different equations. One is the linear and second is the cubic equation. So to declare the system of equation, we have to combine these two symbolic equations into an array. So how do we do that? We have to simply define one define one output variable, that is system equations is equal to, in a square bracket. That's how we define an array. So same way we have to merge, we have to combine this two equation, that is cubic equation and a linear equation. So when I execute my current section, I am able to see that I'm getting the symbolic objects in my workspace window, and I can see I'm getting cubic equation, the linear equation, system equation, which is a 1/2 symbolic object. That's a size, basically how many like variable it contains, x and y. So this is basically we can say a symbolic array. So if I double click on the system equation, I'm able to see I'm having two different equations, which is 1/1 sim. And if you if you double click on it, the value is x cube minus 2x square plus y is equal to 0. So that is how we define equation. We declare variable as a symbolic variable. We define equations, and after that, what we do, we we can combine equations into an array. After that, we can plot. So this basically fplot function, is used for visualizing your equation. So if you search for this fplot, you will be, you will able to see that fplot is being used for, like plotting, plotting the equations data. So what equation we have? So you can see that it's a plot, it plot the expressions or function. So fplot plots the function. So it is a part of basically a symbolic math toolbox if you are going for symbolic expressions, or if you want to plot a simple equation or expression, you can, it is from MATLAB. So MATLAB decides which type of data that fplot function is going to handle. So here in this case, we have defined an equation. Then we have given some other, the spacing parameter that line width is 1.5. And then simple x label, y label, x text, and then grid on, hold on function. Why hold on? Because I also want to add on one more equation within the same plot, because I have to, I have two equation for the given system, and the first is a cubic and second one is the linear one. So that is how I'm adding, one more equation and hold on, and then once I'm done with my visualization, I can release my MATLAB hold command from that holding process. So that is why we have to write hold up immediately once you are done with the data visualization method. So once you click on this particular section, you can see that we are getting the data plotted. So we are getting both the equation plotted for the given system. So to find the solution of the system of an equation, we can select a symbolic equation system. So now I tell you, so this approach was basically using the script, using the commands and functions. So we have developed pretty good MATLAB code, a live script for for defining for defining a system of an equation, that is by using linear and cubic. The same, the same thing, the same operation we can perform by using, by using control and task. So what we can do is we can add a task here. So that is a solve symbolic equation task. So where we can get the values that is from a solution. Yeah. So because when you execute, this particular statement, you are going to get the solution here. So solution is basically the two variable, that is x and y. So it's an analytic solution of equation, a system equation with respect to x and y with the conditions. And after that, we have to select an equation. So equation is going to be a system equation. Which equation you want to consider for for the process. So is it going to be a cubic equation or linear equation or the system equation? So I can say it's a system equation. Yeah. So we will select the symbolic equation as a system equation from the workspace. Yeah, we are selecting. So when I select from this particular option, it is going to be from the workspace only. So we are selecting a system equation. Variables are x and y, and then we have to specify, specify the solver option. Solver options are given like return real solution, return one solution, return conditions, ignore analytic constraint, ignore properties, and expand all rules. And then we have to click on display result. You want a solution in such a format, or you want an equation. Yeah. And this is basically the backend code, which I will hide as of now because we are using, we're using the task basically, yeah, from this particular, so we have created task for, for this particular data, yeah. Now here, now this is auto run. So as soon as you make the, as soon as you make the selection in this particular task, you are able to see, the output immediately in the solution format. So where solution is x, y, parameter and condition, where the complete equation is given, like x of 1, y of 1 is 2, 0, x of 2, y of 2 are minus 2i, minus 8, minus 8i. So it is with the imaginary value. Yeah. This solver is, this particular solver which we have selected a return condition, which returns a real and complex solution. If you want to show only the real solutions and if you don't want to see the imaginary part at the same time, you can select a different, you can select a different solver option, that is return real solution. In that case, you will find only, the real values at the same time. After that, if you like, this is the task, this is a a ready-made task which we are using. But if you want to see the backend code, how this task, how this particular task is, getting executed, how, how we are able to select on different solver types, how we are able to select on the equation, so how it is getting done. So to view the code that this task is using, we can, we can click on this bottom arrow, and we can, we can just get the command, the code basically. So the very first code, like how we are getting the solution here, the solution is getting with the help of solve function. So basically, solve function is a part of a symbolic math toolbox. Yeah. So it solve equations and system. So basically, it consists of different solver. Which solver it consists of? It consists of return real solution, return condition. This mini solver it consists of. In bracket, we have to provide symbolic variable and real values are true. And then we can display a solution, display a symbolic solution, like that. So we are getting, when we, when we execute this particular command, display symbolic solution, we're able to see this particular output. So that is how we can see the backend code. So basically, whatever you are putting in the task, that code is getting generated automatically based on the control which you have selected in your task, and how you can create task by using this particular task option. And finally, what we can do is we can plot the system of equation and the real valued solution which we have recently obtained. And again, we have this system of equation first of all, and then we have the solutions as well, and we are putting everything in the same the same window, and we are trying to visualize it. So that is how we can by using MATLAB and symbolic math toolbox, we can solve a system of a cubic and linear equation using using MATLAB. And here in this case we have used a live editor and task options. So let's get started with a Fourier transform, and then we will see the Fourier transform application, like which are the areas where this Fourier transform is being used, and for implementation of different system in real world as well. So we will see that. So let's first get started with a Fourier transform here. Yeah. So I am going to use some equations, and we will apply a Fourier transform functions on that to calculate a Fourier transform. Yeah. We are going to compute the Fourier transform of common inputs that we use in mathematical terms, such as so this is a table of contents, and how you can add this. You can go to insert, and you can click on this table of contents, and you can add it in this particular manner. So you can just list down what is your workflow, or what all stages you are going to perform in this particular example that is in live stream. So that that stuff you can just add on in the live stream. Yeah. So here we have table of contents where I have defined some common inputs. such as rectangular pulse input, unit impulse, that's a Dirac delta, absolute value, step, a heavy side, constant Bessel of first kind with the NU parameter is equal to 1, and specify independent variable and a transformation variable. So we have taken some common inputs. So let's get started one by one. So first of all, we will go ahead with a rectangular pulse input, and then we will calculate a Fourier transform for that. Here, since we are doing this in symbolic math toolbox, so what we are doing is we are going to define this variable a, b, and t as a symbolic variable. Okay, so for that we have this seems as space a, b, and t, that so which means we have defined a, b, and t as a symbolic variable. Before that, let me clear my workspace window here. I hope I'm perfectly audible to all of you, and if not, you can immediately type in chat box. I would like to adjust my mic at that time. So here we have this symbolic. We have defined a symbolic variable a, b, and t. Then we are writing f is equal to rectangular pulse. Now, from where this rectangular pulse is coming here? So if I go in a search documentation here, we will see the rectangular pulse is available in a symbolic math toolbox. So this MATLAB function returns a rectangular pulse function. Yeah. So we are providing the input values a, b, and t, and then we are calculating a Fourier. So Fourier function. So if you want to see like why I'm searching in documentation, because I want to let you know which function is available with which toolbox. It like maybe some functions are available with MATLAB, some functions are available with symbolic math. It is like that. So if I type a Fourier, the Fourier function is available with a symbolic math toolbox. But if you recall my last presentation, I have demonstrated the MATLAB live script, and where I have computed FFT of a signal, right? So we have computed FFT of a signal, and we have tried to visualize a signal in in frequency domain, time frequency domain, time domain, right? So that FFT function is a fast Fourier transform that is basically is a part of MATLAB, yeah, right? So here when you call this function Fourier and provide your rectangular pulse input, you're going to get the Fourier, it will compute a Fourier transform of that particular equation that's in that particular input, that is a rectangular pulse input, and the output is going to look like this. So this is how we solve in mathematics, right? So when we want to solve when we apply a Fourier transform, so if you want to compute a Fourier transform of a rectangular pulse input, ultimately the final answer is going to be this one. Going ahead with the next input, that is a unit impulse input. It's a Dirac delta. We can also call it a Dirac delta. So here, first of all, we have to define. We have to first of all create one symbolic symbolic equation, that is f, by using Dirac function. So what is Dirac function? So like which toolbox it is available with? So Dirac function is available with. So it is a Dirac delta function available with symbolic math toolbox. So we will provide the value t, because t we have already declared as a symbolic. So that's why we don't need to need to repeat the declaration declaration one more time. So here what we are doing is so we are we are going to first of all like create that unit impulse equation, and then after that we will apply a Fourier transform on that equation, and we will we will get the Fourier we will get a Fourier transform for that. So that is how we can compute the Fourier transform for unit impulse as well. So I will execute this. I click on run section, and I'm able to get the Fourier transform. Okay, so just a second, we have to execute this particular. I'll do that. So we have to first of all execute this section. So we will get that a, b, and t in my workspace variable. And if you see what is this f, so if I click on f, which is a rectangular pulse input, it's a 1 by 1 symbolic. A comma b comma t. So if you put your arrow, it defines the type of that variable and a size as well. And this is your FFT which you have computed by for the rectangular pulse input. Similarly, if you click on run section here, then FFT is equal to 1, and going ahead with the absolute value. So absolute value, how do we define that? So first of all, we have to define the input. So input is like a into abs, so abs function for absolute, and of t, right? So after that, we will apply a Fourier function. We will apply a Fourier function. We'll apply a Fourier function on that f, which is your absolute value, and then we will be we'll able to get the Fourier a Fourier transform for that. So we can compute the Fourier transform for absolute value in this manner. Yeah. So the output is minus 2a upon w square. After that, how we can compute the Fourier transform of of a step function or Heaviside function? Yeah. So first, Heaviside function has been given with symbolic math toolbox. So if you just search for a Heaviside function right here, and you can see it is available with. So it takes a bit time to search for that. So Heaviside, it's a Heaviside step function. It's available with symbolic math. And if I compute a Fourier transform, I can see the output is pi delta of w minus I upon w. After that, let's say we have a constant input. And what is the Fourier transform of a constant input? So run section. So it's 2 pi, 2 pi delta inverse of w into I. And then we have this, one more equation, that is a Bessel of first kind with the nu parameter is equal to 1. So how do we define that? So here we are using one additional variable, that is x. So that's why we are defining it separately in this particular section. So we are declaring that variable x as a symbolic variable. And after that, so f is equal to, we are calling that function a Bessel J. So what that function does? So Bessel J function, if I search for a Bessel function here, so just a second, I copy it one more time, and so it is a Bessel function of first kind of a symbolic expression. So that is with a symbolic. So it is available with both, but you have to you need to think that in how you are going to use it. So since the input is a symbolic input, so that's why we have to that's why we are considering the Bessel J function from symbolic math toolbox, because the input are 1 comma x, and x is your symbolic variable. And then we'll apply a Fourier transform on that. And to simplify it, so what simplified does? So if you if you type a simplify, so simplify basically it gives you algebraic simplification of the of the Fourier transform, of the computed Fourier transform. So first of all, we'll compute the Fourier transform by using Fourier function of a Bessel equation, and then we'll apply a simplify function to get the algebraic simplification. So I'll click on this run button here, and this is the output. So that is how we can use different common inputs on which we can apply a Fourier transform. We are able to get it. There's one more
Suraj,
yeah.
Suraj, just to add here, so after line number 16, if you just remove that semicolon and rerun the section, you can just show them how it is getting simplified, the expression. Yeah.
Okay. All right. I'll do that. Yeah. Sure. Thanks, Anand. So here, like Anand mentioned, so first we will see how it is simplifying the equation. So basically, so let me click on show only the output. So here, the first FFT equation which we are getting, when we apply the Fourier transform on that, it looks something like this. And to simplify it more, we are going to apply that simplify function, and then the final FFT outcome is is this equation. So this is after applying a simplify equation. So that is how we can use simplify function for for simplifying your algebraic expressions. So that is how we do it. So let me change it to output inline. Yes. The last is about we will specify independent variable and the transformation variable. So here basically it is going to compute the Fourier transform of the exponential function with minus t square minus x square so by default here the symbolic variable determines the independent variable, and the w so w is the transformation variable is being used here, and here the symbolic variable is choosing x for that. So here we are defining the symbolic variable. We are defining an equation, and then we are going to calculate Fourier transform Fourier transform of f. So yes,
Sorry, sir.
yes,
Sorry, sir.
yeah.
One small question. You have taken the output. Is it possible to visualize that output as a graph? For
Yeah,
example, heaviside function. Can you please show the heaviside function and the corresponding graph? Similarly, you can also do it for other functions if possible. Output, after taking output, is it possible to show the output? Whether it is possible to see the graph, please.
okay, sir, definitely it is possible, but I would like to get back to on that point after this. Can I do that?
Yes, please. Yes, please. If you have a future plan, then no problem.
Yeah, sure, sir. Sure. Okay. So that is how we can compute the Fourier transform of different common inputs using MATLAB. So going ahead with so next we will talk about the Fourier transform applications. We will see where this Fourier transform is being used, and then later on we'll talk about the Z transform and the Laplace transform. Okay, so the Fourier transform application, let me open the script for that. Yeah. So this is a bit theory about Fourier transform, that it is a mathematical formula that relates a signal sampled in a time or space. So, I can consider that all the participants, are from the mathematical background, and they know this mathematical term, that is what is Fourier transforms. I don't go in theory much, and I would like to switch to the implementation part. So we have this FFT function in MATLAB, because the sir asked me a question that how do we visualize a Fourier transform? Yeah, because the Fourier function is a part of symbolic math toolbox, which computes the Fourier transform for a symbolic equation, right? But if you want to plot plot that particular data, you cannot have a symbolic symbolic expression at the input. Yeah, so for that you go for a FFT kind of thing. So here we will see that in detail. So basically here the FFT function in MATLAB uses a fast Fourier transform algorithm to compute the Fourier transform of the data. So here we are going to consider a sinusoidal signal. We are naming that signal as x. So that is a function of a time t with a frequency component of 15 hertz to 20 hertz, varying in that particular range. So basically we have to define the step size as well, and the time vector or time vector sampled in increments of 1/50. So 1/50 is basically the time step which is in second over a period of 10 seconds. So how we are defining this particular problem statement in a code format? Like we have Ts is equal to 1/50. T is equal to varying in the range of 0 to Ts. So Ts is a step size till 10 minus Ts, and then we are defining the equation, which is a sinusoidal one, and then we are going to plot that equation. So t comma x. So your x level is time. X level is time in seconds, and your y label is going to be the amplitude of sinusoidal data. So now, first of all, let me clear my workspace, and then I will go to the live editor and click on the run section here. Yeah. So here, as you can see, we have we have t and x. The size, the dimension of both the arrays is same, and as you can see, this is your this is how we can plot. Let me try to minimize. Okay, this is the minimize. Okay. So this is how we can visualize a sinusoidal signal that we all know. And if you want to like pop up this in figure window, you can just click on this arrow and you can get that in the figure window. And if you go to file and if you click on generate code, you're able to see the code behind. Yeah. And there are more into it. If you go to tools, you can find out a basic fitting and data statistics here. Like if you click on data statistics, you are able to get the data, get the basic statistics, like you can find out the mean, maximum, median, mode, standard, range, and everything. So if you click on max, you can see the maximum value on x-axis, and if you click on like y, you can find out the maximum value on y. Similarly, mean, so that basic fitting stuff you can perform. Apart from that, you can also data statistics stuff you can perform. Apart from that, if you click on basic fitting here, you can also perform basic fitting on. Obviously, this data may not be in that type, but this is just for giving you an idea that we have some basic fitting option available here, where we have different types of fit like linear, cubic, polynomial, quadratic, and then you also get a fit result in terms of r square value, and it also shows the equation that is being computed on the given data. So that is available with the tools. But apart from that, you can also check for a property inspector option from this particular option. So that is a bit about how we can access this figure plot and its different functionality. So we have plotted the sinusoidal waveform with given input requirement. After that, we'll compute the Fourier transform of a signal. So this is a signal, right? So this is the engineering application of this is the engineering application of the Fourier transform. Because what happened when we are considering a signal, let's say ECG signal, when we consider ECG signal, if a doctor, if a lab technician is generating an ECG signal, out of a patient, then with that ECG signal, we have to analyze something, maybe a heartbeat, and we have to, let's say, we have to check the stability of the person. We have to check the stability of the patient, right? So which we can check that, by visualizing the ECG signal continuously, right? Heart rate, ECG, and everything. So, many times we have to what medical guys does, they collect the data, they observe a data. But we as an engineer, we as a mathematician, what we can do, we can we can apply some research methods on that to analyze the signal completely, so that we can come out with some advanced technology, so that we can make the job of observing ECG signal much more better. Yeah, so that is how we can invoke the engineering application in such a situation. So here, so obviously, when we deal with the signal, we have to deal with different parameter. It could be calculating a frequency Fourier transform. It could be filtering signal. It could be optimizing signal. It could be extracting some features out of the signal. So extracting features mean we may go for statistical feature. We may go for wavelet features and like that. So here, what we are doing is we are computing a Fourier transform of the signal and create a vector f that correspond to the signal sampling a frequency space. So so we are going to create a vector f that is going to be a Fourier transform of the signal, and this f that vector f correspond to the signal sampling in n frequency space, where the frequency spacing and number of frequency spacing is there. So here, let's do that. So we are calculating a FFT first of all. We are getting y, then we have the sampling frequency 1 by Ts, and then we are creating a vector f that correspond to the signal that we are using. So Let's click on the run section here, and we are getting this y is basically a complex double, that is the data type of that particular variable, and which is basically a Fourier transform that we have calculated of a sinusoidal signal. Now, so when you plot the magnitude of a signal as a function of frequency, the spike in the magnitude corresponds to the signal frequency component, which is varying in the range of 15 Hz to 20 Hz. So how do we plot that? We'll plot f comma, so we'll f comma absolute of y. Yeah, so absolute of y means, so if there's any negative value, it will consider the positive one, that is the function of absolute. So next level we have frequency, magnitude, and title is also a magnitude. So let's click on the run section, and this is how we can plot the magnitude of the signal as a function of frequency, which is varying in the range of 15 to 20 Hertz. So signal frequency component. So if you want to observe this in bit detail, you can you can open it in figure window, or you can apply a data label from this particular option itself. So if you apply the data label here, just a second. And able to. So I will apply it here. So it is x value is 15 and y is 250. And the charts are so it also shows the charts properties at the same time. So I can just minimize that, and I can apply a data label, and if I right click, I can go through some properties, delete all data types. So I can delete my data type from here, and I can deselect this option. Yeah. So that is how we can so we can apply that is how we can deal with the signal, and we can compute the Fourier transform of signal. So when we talk about a signal processing toolbox, so where the FFT is very much important, so we calculate the FFT of the signal for various applications. So one example I would like to show you here, that is about a discrete Fourier transform. So where here basically this example is about signal transformation, signal correlation, and modeling. So here this example shows that how we can explore the primary tool of a digital signal processing. Like this, you will find various applications. So this example is from a signal processing toolbox basically. So here we are calculating a discrete Fourier transform. So you can go through this documentation in detail to know more about it. And yeah, so that is how we can use it. So that is one of the applications. So I'm going to share this this document with you in detail, so you can go through in that in detail. So we have seen how we can use Fourier, like what are the various application of Fourier transform. This is one application. Similarly, even in image processing, if I talk about we calculate we apply the Fourier transform in various image processing application when it comes to image pre-processing, filtering, and denoising. So that is also one of the application of Fourier transform that we use in image processing engineering. So after that, let's discuss the Z transform first, and then we will then we will go through a Laplace transform, because like Simon sir mentioned, many of the many of the faculties have they are using this MATLAB tool, and they have implemented various various examples on Laplace transform. So they have so the priority is Z transform. So I will follow that work with that flow itself. So let's see how we can perform a Z transform in MATLAB. So again, this is a live script that we are going to use here, as you can see. Yeah, and just a second. And we have, oh sorry. Okay. Again, Z transform in using MATLAB, you need to have a symbolic match toolbox with you for implementation of Z transform. So here, first of all, we have to So here I have considered some examples which we are going to use, and we will we will compute the Z transform of that. So here, first of all, we'll declare the variable as a symbolic variable, which is n, and after that we will have one symbolic expression, that is f is equal to sine of n. Yeah, so sine of n is your symbolic expression. Yeah, and then after that, if you want to calculate a Z transform of a sine of n, that is your f, you can call the function that is Z trans of f, and you are able to get the Z transform of sine of n. So you click on run section here, and you will get the Z transform is Z into sine of 1 divided by Z square minus 2 cos of 1 into Z plus 1. After that, let's consider the exponential function with m plus n, and if I calculate the Z transform of this particular the equation, it is going to be Z into e raised to power m divided by Z minus e. Going ahead, so we are again declaring two different symbolic variables, that is n and z, and here we are going to compute the Z transform of like a heavy side, which is n minus 3 comma n minus z, and which is the answer is 1 upon z minus 1 plus 1 by 2 upon z cube. So similarly, like here, for your understanding, I've considered multiple examples. This could be simple for you, but this is the right approach, right workflow, that how we can compute a Z transform of even huge equations. And we are again declaring some symbolic variable here, like f1 of x, f2 of x, a and b. And then your f1 of x is your first symbolic expression, which is a exp of x, and second is simple x. And then if you calculate Z transform of f1, f2 with respect to x and a and b, then it is like the final outcome is a upon a minus e, b upon b minus 1 whole square. And finally, the last example is 1 by n. So I'm declaring one symbolic variable, that is f of n. So f of n is equal to 1 by n, and if I compute the Z transform of this particular equation, so compute the Z transform of f of n. So here, which is in Z domain, so you can basically see the Z transform, and at the same time I'm computing the inverse Z transform. So when I'm computing a Z transform, I'm providing f, n, and z, and when I'm computing the inverse Z transform, I have to provide the Z transform outcome, that is f symbolic variable, and z and n. So that is how n to like Z domain, and z to the n domain, so which is like that. So if I click on this run section here, this is your Z transform, which is 1 upon n. Yeah, I will share all these live steps. So basically, what we are doing right after the session, we are uploading this live, all the presentations and documents on a drive, and I guess Dr. Simon sir can guide you on that, how to access this particular resources. So we can discuss at the end of the session. Yeah, definitely. So here, Z transform is 1 upon n comma z. And if you calculate the inverse Z transform, which is again the 1 by n. So that is how we can compute a Z transform of many equations, and at the same time by using IZ transform. So if you prefix I before Z transform, you're able to get the inverse Z transform for the same. That is about a Z transform, which is available with a symbolic math toolbox. So even if you go through a documentation of like symbolic math toolbox, you will get all these examples, because normally what we do, we cover example from documentation itself, because that is easy for even participant to access the resources at the same time or right after this session. So let's 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 have an introduction to our Laplace transform. So basically, Laplace transform converts your integral and differential equations into an algebraic equation, right? So Laplace transform of a time domain signal y of t is defined as Laplace of y of t is equal to y of s, capital Y of s is equal to 0 to infinity y of t e raised to power minus st into dt. That is your Laplace transform. Yeah. So it is basically integral. It converts integral and differential equation into an algebraic one. So if you so we have also attached one PDF here. So basically, this PDF is a math tutorial on a Laplace table. It is basically a hyperlink. So you can use that Laplace table when you are using MATLAB for that. So let me just check. Let me open Chrome and type this so that we are able to see that tutorial right here. So which is an example itself. So when you open example, you will find that link itself. This is a two-page PDF document. It's a complete table of Laplace transform, which you can refer along with some notes as well. So example one is constant or unit step function. So here we will evaluate a Laplace transform for y of t, which is equal to 1, and where t is greater than or equal to 0. So first of all, we'll have to create a symbolic variable for a and t, for a and t, and so how we can do that? So the symbolic variables are sims y of t, y of s. So y of t is your sim of 1. So when you execute this section, you get a y of sim of 1 means 1. So 1 is your symbolic variable. So sim is function to convert a number into a symbolic, symbolic expression. So you can see your y of t is so your y of t is 1 by 1 sim function. After that, we will calculate a Laplace of y of t. So we know that the Laplace of 1 is 1 upon s, and you get that. Then we will consider one sinusoidal function. Y of t is equal to sine of a into t. So how we define that? Seems y of t, y of s, a space t. So y of t is equal to sine in bracket a into t, right? So this is your symbolic expression. Y of t is equal to sine sine at. Yeah. So if you open this, you will get that. Okay, so here the output, we are not storing the outcome, we are just defining that here. So y of t is equal to sine a into t, and now if you calculate a Laplace of y, a Laplace of yt, you can see a upon a square plus s square, and this output you will find into a final y here, that is a upon a square plus s square. Similarly, we have given some example for so that you can try at your end. And if you click on this particular equation, you can go to equation section, and you can put some equation here. You can use different structures for that. So that is how you can you can insert an equation. So if you go to insert, and if you click on the equation, one more tab gets open like that. Yeah. And example 3 is powers of t. So t square we are defining here. So run section, and if you calculate Laplace of t square, you are going to get 2 upon s cube. So that is how it is very simple that how we can calculate, that how we can evaluate a Laplace transform for any equation in MATLAB using a symbolic math toolbox. So after that, we have given, so we are also using a Dirac delta function here. So Dirac delta function is defined as delta of x minus a is equal to 0, where x is not equal to a, and then some conditions are being given. So we are first of all calling the Dirac function. So we are so we are defining y of t is equal to delta of t. So when you execute Dirac of t, you get a symbolic expressions of it as a delta of t. and then if you compute the Laplace of that y of t, you get the 1. So like that, you can see this example. Again, we have a Heaviside function here. So Heaviside function is defined as h of x, where 0 is x is less than 0, 1 by 2 x is equal to 0, and 1 is x greater than 0. So how we can plot the Heaviside function? So first of all, define the x as a symbolic variable. So f plot is used for expression plotting. So f plot Heaviside x, then some limits we have given me x like minimum and maximum, and then line width of 2. Title is Heaviside function, label and h of x, and hold on. Then we have given the command of hold on because we are going to have a scattering plot at the same time, and then we can plot the Heaviside function in this particular in MATLAB. So that is how we can we can plot the Heaviside function in MATLAB. So here we have given like z is equal to, we have given some steps 0, 0, 0, 0 0.5, 0, 1, and then we have we have plotted a scattering plot. So it's 0, 0, 0, 0 0.5, 0 0, 1. It is like that, and then we have plotted a scattering plot, and that is how we can plot the Heaviside function. And after that, we can also evaluate a Laplace transform of h of t minus 1. So for implementing this particular equation, we need to define y of t, y of s, and t as a symbolic variable, and then a function Heaviside t minus 1. You get you get a symbolic expression. Then apply a Laplace on this symbolic expression, that is y of t. You get the outcome. So you can try it yourself. So we have given two Heaviside equations here, and then we can also define a derivative function. So how we compute the derivative of a function? So we can use a function diff diff in bracket y of t of t. So basically, compute a derivative. So derivative of y of t with respect to t. So what is your y of t? So your y of t is basically the Heaviside in bracket t minus 1 into e raised to power a t. So that is how we can compute a derivative, and then we can apply a Laplace on the derivative to get the Laplace outcome of a Laplace transform outcome, that is y of s. So you can try it. And similarly, you can also compute the inverse Laplace transform. Suppose we have y of s is equal to 1 upon s cube here, and then we will declare the symbolic variable, we'll declare the symbolic expression, the Laplace equation, that is y of s is equal to 1 upon 1 by s cube. Since y of s is already a symbolic variable, so it is going to be a symbolic expression here. And after that, if you apply I Laplace on y of s, you'll be getting t square by 2. So that is how we can compute the inverse Laplace transform. So we have seen how we can compute the Laplace transform of different equations. At the same time, we can also apply inverse Laplace transform on that. At the same after that, we have also seen the Z transform and inverse Z transform as well. So let's see how I would like to show you one simple example of ODE because the in detail ODE and PDE is going to be covered in the Friday session. So session will be hosted by Anand and Shovik, which is on Friday. So I'm just going to introduce you the ODE part in a bit. So just give me a moment. I will just go to the yeah. So I'm going to consider a very simple equation just for introduction part here. We have an equation that is a signal order ODE equation that is 2t y is equal to 2t over the time interval of 0 and 5, and the initial conditions are y0 is equal to 0. So here we have to define first of all the time span. So T-span is 0 space 5, that is 0 to 5. Then y0 is a 0, that initial condition is 0. Then we are using a ODE45 solver here. So basically there are different types of ODE solver that we have available. Just a second. We have different ODE solvers in MATLAB, like OD45, 23, OD113, 15S, 23S, OD23T, 23TP. And there are some, there's a problem type, order of accuracy, and when to use this thing given. So we are using OD45 here, which has a medium order of accuracy, and most of the time this should be the first solver tried that has been recommended. So here using OD45. So here how we define the input parameter requirement for OD solver. We are computing, we are evaluating OD equation at t comma y. The equation is d of t. So what is d of t? D of t is your function file which I'm using. You can see f of x in my current folder. So if you click on d.m, so I have defined that 2 into 2 equation here. So that is why here we have defined the function file. That's a format of defining input requirement to the OD45 solver. Then we have this T-span, which is a 0 to 5, and the Y0, which is your initial condition. And it computes the OD, so it compute, OD45 computes this equation, and it gives you the output in T and Y, and then we can plot the data, in 2D plot. So where we have to define T comma Y, comma, some line styles and color code. So when you execute this particular statement, you can see that you are getting some output. This is the OD, this is the OD, this is the output for a single order ODE equation. So that is how you can get started with ODE using symbolic math toolbox. But definitely in upcoming session, you are going to learn ODE in detail, and like where you can where most of your doubt can get cleared. And yeah, so this was just an introductory part which I wanted to let you know. So let's get started with the curve fitting tool. So I'll show you one example on curve fitting, or data curve fitting. So again, there are two approaches basically. The first approach is we can create a live script for implementing curve fitting algorithm. And second thing is we can use the CF tool. We can use curve fitting tool for the same. So let me just go to the so here we will perform a simple linear curve fitting by using the approach. So first of all, what I'll do, I'll simply take the data from here. This is simple MATLAB script. I would like to show you the demo of example itself. I will be taking through your demo. So here, what I'm doing is, so let me just quickly go to new and open one live script. Yeah, and I will get this three lines of code here. Yeah. Okay, so let me save it as a linear fit. Okay. So we are generating some random data which has somewhat linear profile. And how we are doing that? X is equal to rand function we are using, which generates a random number in the range of 1 and 100, which is this dot multiplied by a 10. And yes, so when I execute this, I get this capital X, which has this data, which has somewhat a linear profile basically. If you want to plot, you can select the variable X, you can go to plots, and that is how you can plot it. Oh, it's better to have a scattering plot. So the scattering plot is just like this. Yeah. It has a linear profile, as you can see. After that, we will add noise to make data more random. So how we are adding a noise? So we are using this rand_n function, with the same, with the same dimension, that is 1, 100, and then what we are doing is we are computing y with the equation of a line, that is 2 into x plus 5 plus noise. Yeah, this equation shows the linear profile, and we have added some noise to make it more randomized. So here, the whole this section gives you the y, which is the output of equation of a line. After that, we will perform data visualization. So I'll just click on a section break. Oh, sorry, not here. The last, basically a last line, and then section break. For data visualization here, so let me click on run section here. So this is your data, which has somewhat linear profile, as you can see. Yeah, and after that, what we will do now, so what we have done is here, so far we have simply generated data which has somewhat linear profile, and then we have computed the equation of line by using 2x plus 5, and we have added noise, and we are visualizing it. Now, to fit this data on a linear profile, to apply a linear curve fitting on this particular data, we have to compute the constant. That is, what is the equation of a line? Mx plus mx plus c. So we have to compute m and c, two constant. So how we do that? We have to use this LSQ curve fit function for that. So basically, LSQ curve fit function is a part of MATLAB. So if you search it in search documentation, you will able to see it's solve a nonlinear curve fitting data fitting problem in the least square sense. You can have a detail of documentation later on, and here the input requirement. So let me just take it here. So we have to again click on section break. So here the input requirements are like this. So we have constant is equal to LSQ curve fit f. So f is your function file basically, which is already in current folder. And what is in that? So we have defined the equation of a line. So y is equal to f of constant comma x2. So y is equal to constant of 1 into x2 plus constant of 2 and a. So that is a simple equation that we are calling here. Initial conditions are 0 for x and y, and your data. So data is your y. So y is your this data and the x. Yeah. And then m is equal to constant of 1, constant of 1. So this basically LSQ curve fit will give you the m and c are two constant values. So that for that reason we are using this LSQ curve fit equation here. So if you click on run section,
Suraj, just interrupting for a minute.
Yeah.
So there was a comment in the chat window. So someone wanted to know about how they can design their own function. So since you opened up that function f, so if you can just briefly say the argument, what is the input and output of a function, and I've also posted one link later. We can show that link also with some other examples. Yeah.
Okay. Thanks for that. I will show that. Yeah.
Thank you.
Yes. How we can create a function? Let's see that. So if you go to new option in the home tab, you will find another two options. The first is live script and second is a function. Function and second is live function. These two options you will find. So if you want to create your own function, you can use any of these two. So I'll click on the function. So if you click on the function, it will open the basic template for creating a function file. So how we can differentiate which is the function file and which is a simple MATLAB script from this icon. So fx icon is always a function file, and a MATLAB script icon is always a simple MATLAB script. And this is how we can differentiate simple MATLAB script and live script. So it is somewhat different in graphics, right? So here we have this function file. So basic template is our very first line is name of the function, list of output parameter, then the function file name which you have to define, and list of input parameters, and then the end function. So what you can do is, let's see, I want to create a function for addition of two numbers. Just a basic idea I want to give you. So I can define y is equal to x plus, let's say, x plus z. That is my equation. So accordingly, I have to change my output argument. So my output argument is y. Since it is a single output variable, so I cannot use. It's fine if I don't use that square bracket, but if it is more than one variable, you have to enclose it in a square bracket, and then I can say the equation is arith. So arith equation, I'm performing arithmetic operations, so that's why arith equation here. And after that, here I have to provide the inputs. So inputs are x comma z, and now you have to click on the save option. So when you click on the save option, if you see file name, it is same as your function name. So that is how it happens. When you click on save when you click on a save function, it automatically takes the function name as a file name, because obviously that is the unique name of the function which you are creating, and with that only that function is going to be called. And let's click on save here. And now how do we call that function? So as I know that the input variable requirement of these functions are two. There has to be a two input variable. One is x and second is z, right? A two variable. So let's see, I want the output as, so I'll define one output variable. So arith arith solution is equal to, what is the function file name? Arith. Is it opened in current folder? Yes. So I can type initial 2 or 3 letter, and I can press the tab button. So as soon as I press the tab button, it recommends me something. So I have this arith equation function file, which is available with my current folder. So I can press the enter key button there, and then in bracket, when I have to provide the input parameter requirement, which is a 4, 5, for example, and then execute. So I'm getting an answer 4 plus 5 is 9. So what it is doing, so when you call that function, it goes to the current folder, it goes to that function, and it performs the it performs the task of addition of two number. It comes back to again your MATLAB command prompt, and the final variable will be posted in the arith solution. Similarly, you can use a live function here. So live function is a bit different. Again, it's a combination of script and like text and code. So here also I can what I can do is I can provide arith alive, yeah, and save this function. And if you click on to provide 5, 6, it is going to give you an answer. So that is how we can create our own function file just like this, using simple MATLAB function or MATLAB live function, and you can call it in your main command file, and you can execute your whole statement. Yeah. So that is how we can. So here what we are getting is we are getting the value of m and c, which is 0.49 and 43. So here I'm getting some warning, which is basically not acceptable. So let me just check x comma y if it is possible. Okay, and okay, I'm not getting any negative value here. Just give me a moment. Okay, so here basically here we have to we are using this ls2 curve fit function for calculating the constant m and c, and then what we do is we basically again we are going to fit that data by using the constant m and c. So we are going to apply a linear curve fitting on the input data. So let me click on section break here, and here what I'm doing, I'm creating one variable xbit with I'm creating an array basically, which is varying in the range of 0 to 10 with a step size of 0.01, which gives us array with type double. And here I'm running that app function on constant and xbit so that I can apply the linear curve fitting on the input data. Okay, because my input data is input data. So I have input data which I have taken initially. I've computed the value of m and c. Now I will apply the value of m and c on the input function so that I can perform the curve fitting. I can perform the data fitting, and after that I can visualize the output. So my x comma y are the original data, x fit and y fit are the output data. So if I click on run section, I will get the curve fitting output in this particular manner, as you can see. Yeah. So this was the live script approach that we have followed here. Same thing can be done by using app. So basically, we have an app here that is the linear curve fitting app. Sorry, not linear curve fitting app, the curve fitting tool. So here we will go to this match statistics and optimization. You will find this curve fitting tool here. And yeah, this is your curve fitting tool. And here you can select out X data, Y data, and Z data. And I'll select the X data here. So a capital X, Y is your capital Y. And as soon as you select out the data, it gives you the curve fitting done. So if you see the value of P1 and P2, why P1 and P2? Because we have, it is this tool has selected default polynomial degree 1. But if you see the value of P1 and P2 constant, it is 1.966 and 0.099. Similar values we are getting here when we have applied that function. M is 1.9660 and C is 5.099. So we are getting the same result. But add-on option here available is we can compute the goodness of fit. So we can compute the entire goodness of fit along, so where we can observe what is SSE, R square, adjusted R square, RMSE, and so on. If you explore different algorithms which are available here, I can go to interpolar, linear fitting, polynomial power, and so on. Yeah, I have so many options. And if somebody is doing research in curve fitting, and if they have, if they have created their own equation, if they want to, like develop their own custom equation on curve fitting, they can click on this custom equation option, and they can write an equation like m into c, m into x plus c. Yeah, so this is my custom equation which I'm writing, for example, and I'm getting the entire goodness of fit and everything. So that is how I can use the CF tool app for curve fitting. And if you go to file, I can generate MATLAB code for this curve fitting, for this linear curve fitting, which means whatever selections I have done now in this particular tool, it will generate the code for that, and I can save this session. I can save this MATLAB session for the same. So that is how we can use CF tool app for better understanding and making your task more interactive by using linear curve fitting. At the same time, you don't need to write commands for evaluating the goodness of fit, because as you can see, we have around 5 to 6 parameter, and again, you have to call each and every each function, each of these functions to calculate SSE, R square, DFE, and so on. So that is the advantage of using the tool like CF tool, which is a readily available app for implementing different curve fitting methods. At the same time, you are able to generate the code. So that is how we can use MATLAB for for defining system of equations. Fourier transform, we have also tried to understand the Fourier transform equations, and then Laplace transform. We have understood Z transform. The ODE part in detail will be covered in the in the Friday session. along with the PDE. And then I've also tried to, like give you some idea about a curve fitting tool. So that's it from my end. That was my agenda for today's session, and I hope I was able to cover of what the given agenda. And now I would request participants to put your query in the chat box. So we have another 9 minutes left where we can discuss the questions. Thank you.
Sir, thank you. I have seen a few points to give here. Am I audible?
Yes, sir.
Number one, you have used ODE 45, ODE 23. That is something new for us. We always use the desolve function for solving the second order differential equations for getting analytical solutions. So you didn't mention about desolve, and you have selected one differential equation which is first order. Whether this ODE 45, ODE 23, they are usable to solve the first order ODE alone, or they can be used for second order ODE. That's my first question.
Yeah. They can be used for solving, sir, second order ODE as well, because the next, sorry, this is not symbolic one. So next example which I have is basically on the second order ODE. Where is that? Yeah. So where I have used this ODE 45 for solving second order ODE, but before that I have some, I have to use some commands. So definitely you can use ODE 45 for second order ODE as well. So basically there are different types of ODE functions, sir, and based on the problem statement and based on the user requirement, you have to make a choice. So the ODE 45 is the most common selection, and it gives you a medium type of accuracy. That's why for this example I have selected the ODE 45.
You have mentioned some initial condition. Is there any initial condition and boundary conditions? Some, what is that 0, 20,
Yeah, these are the initial conditions, sir. So basically, this is basically what we have done. We are rewriting the second order ODE as a first order ODE, and then we are using this MATLAB function to convert my system as a MATLAB function, because initially we are defining it as a symbolic variable. Yeah, and then I'm defining the initial condition here, 0, 20 and 2, 1. 0, 20 is time span, sir, and 2 and 1 are y1 and y2, and then I'm computing the ODE, and then I'm able to get the ODE plot at the end.
Okay, sir. And now the second question is, after Z transform, solution of differential equation you have missed, or you have any plan that you will make it on Friday? Same
Yeah,
thing,
definitely.
solution of difference equation using Z transform, and the solution of differential equation using Fourier transform. This gap, can you please
I have
the
explained one example today, sir. Differential equation
using Laplace transform you would have explained, which already our faculty know that. But what is the MATLAB code for solving differential equation using Fourier transform and difference equation using Z transform? If you have time, you can cover up, or you can ask the other team members to cover it on Friday.
Yeah. So Friday I will definitely, I will give this feedback to the resource person who is on Friday, and I'll ask them to cover this point. Solution on differential equation using ZT and Fourier transform. I'm sorry for my typo mistake.
That's okay, sir. Any other questions, audience? Please post your questions in the chat box so that you can answer. I forgot to ask this. I made a request to show the graph for Heaviside function. Do you have any graph that I can show? Sorry, what is
Actually, sir,
h of t minus 1? What is t plus 1? H of t plus 1 and what is h of t minus 1? Can you show it in graph?
actually, sir, I don't have an example right now, and I was not able to compute it. So it's better I can send you, some examples on that. So just give me some time. I will post, I post some link to you on WhatsApp or maybe on email, and I will give same feedback to my, colleague for a Friday session. But definitely, I'll come back to you on that. And how do we plot?
Suraj, one thing to just add for this question.
Mhm.
So today we have seen two types of plotting. So just to means Suraj has shown the normal plot where he's using the plot function, and also when he's trying to plot some symbolic variable or function, he's using fplot command.
Yeah.
So so if you can open any of the script where you were
Yeah.
computing the Z transform, yeah.
So you can
Or even the
also
first, yeah, the first script can also be, yeah, okay, Fourier transform, yeah. So if you run any of the section here, maybe the heavy side one will only do. Let's see.
Yeah.
So after the section is still running, so we have
Okay, just give me a moment.
cleared the workspace, or maybe.
Okay, it's done. Heavy side you're talking about, right? Yeah, it's executed.
Right. So if I'm not wrong, Professor was asking me whether we can plot this in some way. So using the fplot command, I guess you have to just mention the function name. And
Am I correct?
I think so. You can also enter the limits if you want, but for the time being,
Yeah, that additional things can be done. I think it's still executing.
So sir, today I shared the file, one file, MATLAB file. I mean the Word document. Maybe I sent the file name is visualization. Can you please open it in your screen?
Just a second. So let me just stop sharing for a while.
In which there is one good example through which you can see the output of a Fourier transform. At the same time, the graph of the f of w. That will be useful for ECE and EEE research scholars. And for the mathematics department, let's say one of the main function, that's the first problem we used to solve it in our first Fourier transform class.
okay, sir.
Yeah, I'm sharing my screen. Yeah, can you see it?
Yes, yes. See here, here I have given some functions, basic functions, units of function, heaviside functions. These very basic definitions and examples we need to communicate to our research scholars as well as the faculty members. Yes, you can see that the first problem. Yes, this is a simple problem you covered already. These examples, you already covered this experiment 1 and 2 examples you covered. Please come down. This all we have covered, heaviside. Yes, this is all simple. Yes. You can please come down. This is inverse Fourier transform. Okay, no, the last visualization. Yes.
This one?
Just go up, sir. Just go up. Go up. Yeah. Stop, please. Yes. This is the first problem we used to give to our students to solve the Fourier transform after introducing Fourier transform definition. It's a continuous function. To say analytic solution is given. Please scroll down a little bit.
Yeah.
The analytic solution of the Fourier transform of the given function is given. No, scroll up, sir. Scroll up. Please scroll up.
Again.
Please scroll up. Last. Yeah, please stop. See here the output of the function 2 into sine omega a by omega. This is the output of the Fourier transform, but how to visualize this function 2 sine omega a by omega? For that, the program is written, which I found it in a book, Advanced Engineering Mathematics by using MATLAB. Please scroll down, and the author has written MATLAB coding. Please scroll down, and that function can be visualized using this coding, MATLAB coding. Please scroll down. Please scroll down, and the output. This is what the output we see. The first one is nothing but a graph of the function f of w. So similar type of graph we need for different functions and the corresponding Fourier transform. So instead of giving in our mathematics class, whenever we solve it and give it as a f of w, students may not be happy. But when we give output as a the function f of w is a graph, definitely that will create interest. And if they know the application, it is applied in electrical electronics engineering, students will be very happy and they'll be attending the classes with interest. So maybe in this next section, if possible, if you can able to add such output, just finding the Fourier transform of Heaviside function and Heaviside t plus 1, t plus 2, what is t minus 1, what is the corresponding its graph. If you can cover up those areas, that would be very great help for us. And
thank you, sir. Yeah, you will do that, sure, to visualize the output as well.
Yes, yes, yes. That's why I sent the material in advance.
Thank you,
sir. In the next, in the next question, please cover some topic problems this time.
Yeah.
Any other questions from the research scholars and the faculty members?
Okay, so definitely, sir, we are taking a note of this. And since Anand is also here, so definitely, sir, like Anand mentioned, we will present out those things in the next session.
Also, Suraj, if you can go to that Laplace file, so there is one example on that Heaviside function and how it is plotted. So just I wanted to emphasize on that f plot thing.
I think we haven't used the f plot comma. Yeah, this one, right?
Yeah, this one. Yeah. So I think this will answer to some extent what professor is asking. Like suppose we have the function defined and we want to plot the function as well. Then instead of the normal plot command, which is used to plot the variable stored in the workspace in the form of vector array, row vector or column vector, here we can plot actual functions or symbolic variables. Like x is a symbolic variable, and using the Heaviside function, we have defined another symbolic function, and we are plotting that function using that fplot command, and we are giving the limits of the range of the x-axis from -2 to 2. So if you scroll down just to show the plot range, the x-axis, yeah, so it is the plot is from -2 to 2, so that has been provided inside that fplot function, and the rest are just line width and the width of the line. So in similar way, so whatever is the function, using the function plot. So here we are plotting a function using the fplot command. You can plot them and visualize them. So I hope this is going to help. Yeah.
Okay. See, Suraj, here you can do one thing. H of x is there, no? So you can give a graph for h of x minus 1, h of x plus 1, how the graph changes. Is it possible to change or use some slider function to visualize graph as we change the value? Because that is required to solve certain Fourier transform problems.
Definitely, sir. What can be done, Anand? We will modify this example with some task and controls, and we can share it with the sir, and so that he can share with all participants. Can we do that?
Yes, yes, definitely. That can be done. So thank you for the suggestion. We can definitely include those sliders and modify it and change the parameters to visualize at different cases.
Thank you, sir. Thank you.
Okay.
And you see the even please scroll up a little bit. No, just down, sir. The function h of x only I'm talking about. Please show the h of x function.
Yeah.
See, the h of x function, somewhere I saw a function like 1 minus x square into some h of x function. So wherever you use h of x along with the other functions like exponential or trigonometry, such example also you can take it and show how we can take Fourier transform and the corresponding output as a graph. Okay, sir. Can you understand what I'm trying to say?
Yes, sir.
That's why I sent the Engineering Mathematics 3 book fully. The full copy I have sent to you. You can please go through the problems for a transform of a square minus x square. Many problems are there. We will discuss in a separate meeting.
Yeah, that can also be done.
Yes,
so
yes.
yeah,
We will have a separate meeting before Friday, so that we can cover up this area. Is there any question from the research scholars and the faculty members? You can post. Suraj, can you please share your email ID so that they can send the questions if any?
Sir, I have also attached my, I have also posted a feedback form link. So I request everyone to please fill this feedback form. It's a post-session form actually, and I'm also posting my email ID. So I request everyone to please, fill this post-session form, because this will really help us, adding, working on our contents and modifying examples like we discussed today. And this is my email ID. You can email your queries, if any, on this email ID.
Thank you, sir. Thank you, Suraj sir and Anand sir.
Yeah, thank you, Professor Simon. And
Thank you, sir.
Please fill the feedback form. You can give your comments and how you are using mathematics in your domain. You can mention that too. So it would help us in the future sessions.
So I would like to thank the management and Dr. Chancellor Dr. Elizabeth Varghese, Pro Chancellor Anand Jacob Varghese, Director Ashok Varghese, Vice Chancellor Dr. Sridhara, for permitting us to attend such a program to enrich our knowledge. I thank the faculty members and research scholars and the MathWorks team for accepting our invitation to conduct such a faculty training program. Thank you so much. Thank you, everyone.
Thank you, sir. Thank you.
Thank you, sir.
Research scholars, faculty members, you can leave.
Okay, so sir, shall I
Yes, sir.
end this meeting for all?
I think 5 o'clock, Jonathan told that there's a meeting with the Vice Chancellor.
Okay.
With the MathWorks team. As we
there will
have
be a separate
completed the
meeting,
meeting little early.
Yeah, there will be a separate meeting.
Are we going to meet the same platform or some other MS Team platform?
Anand can give you
So
the
that will be on MS Teams platform. Yeah.
MS Team platform. Then we can leave this meeting?
Yeah, we can leave this
Yes,
meeting.
sir.
Yeah.
Whether the meeting link is sent through mail, sir?
Yes, I most probably.
Okay, sir. I'll check the mail and come back to you. Bye.
Sure, sir.
Bye, sir.